you probably heard of the golden ratio or phi before, and it's approximately 1.618. But how is the golden ratio actually defined to be this number? Well, one definition is that it's the ratio between successive terms in the Fibonacci sequence as the numbers in the term get bigger. Or actually it works for any sequence that is generated by adding together the previous two terms in the sequence. Okay, that's a definition. What else is there? You might know the really interesting continued fraction of the golden ratio, which is full of ones. 1 plus 1 over 1 plus 1 over ... It just continues like that. This is the golden ratio. And if you replace that part all over there, and you can simplify it down to 5 minus 1 over 5 equals 1. Well, I just rearranged the terms a little bit. And so, yeah, you've probably heard of this property of phi before. At least some variation of this. For example, phi equals 1 plus 1 over phi. That's a property. And if you put x instead of phi and you solve for x, then you get the exact value of phi, which is 1 plus root 5 over 2. So, that's the definition of phi, right? Well, sort of. Because we're missing something. What is it? Well, it's the other golden ratio. So first, let's look at the Fibonacci sequence. It's generated by adding together the previous two terms to get the next one. But why not go in the other direction? Why not find a number such that when it's added to the first number in the sequence, so 1, it gets 1. Well, you get 0. And then 1 plus 0 is 1. Negative 1 plus 1 is 0. And you can see we start getting negative numbers. And this is the sequence that we get. Now, where does the golden ratio come from again? Yep. Take the ratio between the previous two numbers. And you can also do it for the other sequence. And what do you get? It actually approaches the other golden ratio that I was talking about. Yeah. And you might notice something quite suspicious about the digits, because the first 5 digits after decimal places are exactly the same. 0.61803. And in fact, they are actually exactly the same if you go on forever with the sequence. As you can see here, this is the golden ratio and this is the other one. The decimal places are exactly the same. And if we look back to the Fibonacci sequence, you also notice that the terms that we found when we continued backwards are actually the exact same numbers, except some of them are flipped to be negative. To be exact, every second term is negative. Using this fact, we can already figure out the other golden ratio in terms of the first golden ratio. How? Let's check it out. So the golden ratio is the Fibonacci term x divided by the term before it. It approaches the golden ratio. But then the other one, instead it goes from the lower golden ratio, the negative of the lower golden ratio in fact, and then divided by the positive of the larger one. So Instead, you get negative 1 over phi. So that's what the other golden ratio is in terms of the first one. And you can also see that the golden ratio actually has some properties that go with the other golden ratio. So golden ratio minus 1 over golden ratio equals 1. That's the property that we've seen. But we can replace that in negative 1 over phi, as we've seen before in the last slide. It's the same as the second golden ratio. So golden ratio plus the second golden ratio is 1. So the other golden ratio is also 1 minus the golden ratio. And that's why you get all those similar digits. Or I should say same digits, except for the first one, because there's a 1 there. You can also apply this fact the other way around. The other golden ratio minus 1 over the other golden ratio is also equal to 1. And then you can replace 1 minus the other golden ratio. You can also replace that with the normal golden ratio, which is, so you get the other golden ratio plus the golden ratio is 1. So the golden ratio is 1 minus the other golden ratio. And you can check that for yourself. It works. In fact, anything that works with the normal golden ratio can work with the other one. They basically work either way around. So now let's turn to the equation x minus 1 over x equals 1. How do we solve this? So first we multiply it by x to get x squared minus 1 equals x. Rearrange it so that we can put it into the quadratic formula. X squared minus x minus 1 equals 0. And then we can just plug it in. And then we get 1 plus or minus root 5 over 2. If we choose to add it, we just get the golden ratio. But what if we choose to subtract it instead? Well, you guessed it. It's the other golden ratio. Golden ratio pretty much has the exact same properties as the other golden ratio. So there's actually not much difference between them besides the fact that one of them is a different number to the other one. They have the exact same mathematical properties.